Hi, welcome to my channel. In today's video, I want to discuss a very important problem in quantum mechanics, which is the particle in an infinite potential well. So this video is going to be a bit long because I'm going to solve the Schrodinger's equation, I'm going to obtain the wave function solution, and I'm going to discuss all the information related to this particular problem. So let's get straight into it. Now the problem is very simple. There is some kind of a particle which is stuck in a region, let's suppose, and we are only going to discuss the one-dimensional motion associated to this particle. So let's suppose that this particle can only move in the x-axis. This is going to make our problem much easier. Three-dimensional problems are a little bit more complicated. So let's suppose that this particle can only move in the x-axis between the points, let's suppose x is equal to 0 and x is equal to L. At x is equal to 0 and x is equal to L, let's suppose there is some kind of an impenetrable barrier. There is a barrier that this particle cannot penetrate through. So we say that the potential at x is equal to 0 is equal to infinity, and the potential at x is equal to L is also infinity. So the potential beyond x is equal to 0 for all values less than x is equal to 0 is infinity, and the potential beyond x is equal to L for all positive values is infinity. So the potential between these two boundaries is 0 where the particle can exist. So the particle is a free particle in this region between x is equal to 0 and x is equal to L. This is a very simple problem, and like in quantum mechanics, whenever we encounter problems like this, we start with the most foundational pillar of quantum mechanics, one of the most foundational pillars of quantum mechanics, which is the Schrodinger's equation. So the equation that we have right now on the screen is the general form of the Schrodinger's equation, which is also known as the time-dependent form. Now this equation is a little bit difficult to solve because it contains partial derivatives, it contains potential as a function of x and t, and it also contains wave function as a function of x and t. However, because our problem is quite simple, we can actually transform this equation to a much more simpler form. What we can do is we can convert this time dependent equation to a time independent equation. So the time independent Schrodinger's equation looks something like this. So in this time independent form, the time dependence has been removed from the potential as well as the wave function. Now this substitution can only be made in very specific cases. I need to mention that it can only be made when the potential is independent of time. So the potential can only be dependent on space, but it has to be independent of time. So when the potential is independent of time, which clearly in our case the potential is absolutely independent of time, we can start with this time independent version of the Schrodinger's equation, which is much more simpler because it does not contain partial derivatives. Also, it is very important to note that the solution of this time independent Schrodinger's equation is psi x, which is also known as Eigenfunction solution. Now most of the times people, even me, we refer to psi x as the wave function, but to be technically correct, the solution of the time independent Schrodinger's equation is the Eigenfunction solution, and the actual wave function is in fact the solution of the general time dependent form. So the actual wave function is this here, which is a little bit different symbol from psi. So this is the wave function that we are interested in, which contains not only the space dependence but also the time dependence. Now what is the relationship between this wave function, which is a function of x and t, and this eigenfunction here? The relationship is quite simple. The wave function is basically a product of the eigenfunction psi x and expression that contains the time dependence e to the power minus iet upon h cross. So this is the actual wave function solution of the Schrodinger's equation. Now converting a time dependent Schrodinger's equation to a time independent Schrodinger's equation is a completely different topic, and I'm not going to discuss that here. I have actually done a video on it. If you're interested, you can take a look at that. So because our problem is so simple, because the potential is independent of time, instead of starting with the time dependent Schrodinger's equation, we can straight away start with the time independent Schrodinger's equation, which is in fact what most people do. However, it is important to remember that the solution of this time independent Schrodinger's equation is not the actual wave function. It needs to be multiplied with this particular term to make it the actual wave function. So let's begin the problem. So we start with the Schrodinger's time independent form. Now this equation basically contains the potential here, right? So what is the potential? For the sake of definition, we can say that the potential is simply, it can have two values. It can have infinite values for x greater than equal to L and x less than equal to 0, and it has 0 values for x less than L and greater than 0. Now I already told you that the particle is restricted only in this particular region. So we only need to apply the Schrodinger's equation to this particular region. Beyond it, the Schrodinger's equation will only give us solutions where the solution is equal to 0 here and the solution is equal to 0 here. The wave function does not exist beyond x is equal to L in the right hand side and beyond x is equal to 0 in the left hand side. Why? Because the potential is infinite. The particle cannot penetrate through it. If it was a non-zero wave function, then it would mean the particle has a probability of existing there, but the particle does not have a probability of penetrating the barrier in this direction or in this direction. Therefore, the wave function solutions there are 0. We are only interested in this particular region, so we are going to apply the Schrodinger's equation only between the limits of x is equal to 0 and x is equal to L. So in this region, the potential is nothing but 0, right? The potential is nothing but 0. So now the equation becomes much simpler. Minus h cross square upon 2m d square psi upon dx square is equal to E psi. If I take the terms to the right hand side, this becomes minus d square psi upon dx square is equal to twice m E upon h cross square psi, or if I take this to the right hand side, this becomes d square psi upon dx square plus twice m E upon h cross square psi. Now this is a differential equation that is quite easy to solve. However, there is this particular term here where energy is represented by E. Let's assume that this is some kind of a variable which is called k square, so that k is nothing but square root of 2m capital E upon h cross square. Let us remember this as point number 1 because we will refer to this later on. So the equation then simply becomes d square psi by dx square plus k square psi is equal to 0. Now this is a standard differential equation that has a solution that is basically psi is equal to a sine kx plus b cos kx. This is the solution of a general differential equation of this particular form. Now we can prove that this is indeed that solution by doing a backwards differentiation. So if I say psi is equal to a sine kx plus b cos kx and I take a derivative with respect to x, then it simply becomes a cos kx plus kb, and this is basically minus kb sine kx. If I do another derivative of psi with d psi by dx with respect to this, then this becomes k square a sine kx minus here minus k square b cos kx. If I take the minus k square term out, I end up getting a sine kx plus b cos kx, which is what? Which is this particular expression. So this I can write as minus k square psi, or I can now say d square psi by dx square plus k square psi is equal to 0, which is nothing but this equation that we started with. So therefore this is the solution of this particular differential equation. Now here, what does A and B represent? A and B are some kind of a constant whose values are unknown. Now if I want to determine what the values of A and B are, I need to apply some kind of a boundary condition. So I'm going to apply some boundary conditions to find out A and B. Now what boundary conditions can I apply? As I already told you, the particle is restricted in between x is equal to 0 and x is equal to L. Here the particle cannot penetrate, so whatever solution of the Schrodinger equation is 0 here. Here the particle cannot penetrate. The particle can only have some non-zero wave function solution in this region. So at this particular point of x is equal to 0 and x is equal to L, I'm going to assume that this particular solution psi is 0. So I'm going to say that psi at x is equal to 0 is 0. Why? Because at x is equal to 0, the potential is infinite, so the wave function cannot exist. The wave function, and this is the space dependent part of the wave function, so that also cannot exist. It must have a value of 0. So if I apply this here in this, let's suppose equation number 2, if I apply this in 2, I simply get a sine k multiplied by 0 plus b cos k multiplied by 0 is equal to 0. Now what is sine 0? Sine 0 is automatically equal to 0, but cos 0 is not equal to 0. Cos 0 is equal to 1, so cos 0 is simply equal to 1. So I end up getting b is equal to 0. So if b is equal to 0, then I can again write equation 2 in a new form, that psi is equal to a sine kx. So this is the new form of the eigenfunction solution. However, even this is not enough because I need the term a. Now let's apply the second boundary condition that I said x is equal to L and see what sort of information I can come up from there. So if I apply the second boundary condition where psi at x is equal to L is also equal to 0, because there the particle encounters the impenetrable barrier where potential is infinite, so wave function is automatically 0. So there, if I say, I can write this as a sine kl plus b. No, this term is not there anymore because now this new expression does not contain the b term. So here this is simply straight away equal to 0. Now because a is a non-zero constant, it has to be non-zero, otherwise the wave function cannot exist. So I can say sine kl is equal to 0. Now what is the significance of this? Sine of something is equal to 0. Now what does that mean? If you look at the sine function, the sine function can only be 0 at theta is equal to 0. It can be 0 at theta is equal to pi, it can be 0 at theta is equal to twice pi, it can be 0 at theta is equal to thrice pi. So sine 0 condition basically gives us, or sine theta condition basically gives us theta is equal to 0, pi, twice pi, and on, also in the negative axis. So I can say plus minus. So here I don't need to say plus minus, but here I need to say plus minus. So basically this condition tells us that KL is equal to either 0 or plus minus pi or plus minus twice pi or plus minus thrice pi, and on. Now in this particular case, k is equal to 0 is not allowed. Why it is not allowed? It is not allowed because if I put KL is equal to 0, then here this entire expression will become equal to 0 and I'll get psi is equal to 0. Now that is not possible because that would mean that the particle has suddenly vanished, and I don't want the particle to suddenly vanish out of nowhere for no reason. So therefore I can say that this condition is basically not allowed physically. So what do I get? The remaining thing I get is basically I get KL is equal to, let's suppose, n pi upon, so if I take the L to the other side, I get n pi upon L, where n can have values of 1, 2, 3, 4, and so on. Now you will see here, you will notice that I have basically merged the negative terms or basically removed the negative terms, because here if you see the negative minus sign of negative does not give us any new information. So basically if I say sine of minus kx, this is simply minus sine of kx. So wave function is basically the same. It is the same expression. It just can have both positive as well as negative values. So let me include this negative sign into this particular constant and know that the wave function can have both positive and negative values. I'll elaborate this later on. So basically I here say that this particular k is this expression where, let me refer to this as kn because it depends upon n, where n can have values of 1, 2, 3, 4 and on and on. It can have infinite values. So if I substitute this in my wave function, original wave function, then finally I have the eigenfunction is equal to a sine n pi upon L x. All right. So now the first thing I notice is that, first of all, of course, I have not yet found out a, so that I have to do something about that. But this wave function can have infinite values because n can take values of 1, 2, 3, 4, 5 and on and on and on. So this wave function can have basically infinite expressions, and therefore this there can be infinite wave functions possible in the same problem. I'm going to elaborate this later on, but just now for the time being, let us concentrate on this particular a. How to find a? We can find a by normalizing the wave function. So we need to normalize the wave function. Why do we need to normalize the wave function? Quite simply put, we need to normalize the wave function because it is not just enough for the wave function to satisfy the Schrodinger's equation. The wave function must also satisfy another condition, which is known as the Born's statistical interpretation. The Born's statistical interpretation basically tells us, quite simply put, that if you have a wave function solution and you take its complex conjugate and you multiply it with a wave function and then you integrate this between 2 points, let's suppose x is equal to a to x is equal to b, then this basically gives us the probability of finding the particle in between these two locations. Now if I change a and b to minus infinity to plus infinity, that means if I look at the probability of finding the particle from minus infinity to plus infinity, which is basically the entire universe, then the particle must exist somewhere. So therefore this must be equal to 1. Now this is a condition that all wave functions must satisfy, apart from satisfying the Schrodinger's equation. Why? Because otherwise we cannot use that wave function for a real particle. The Schrodinger's equation is a differential equation and it can give us in fact it can give us infinite number of mathematical solutions. However, not all mathematical solutions are realistic. Not all of them can be actually applied for a physical particle. Only those wave functions or those solutions of the Schrodinger's equation can be used for a real physical particle where that particular wave function also satisfies this particular Born's interpretation. Now because in our case the particle exists only between x is equal to 0 and x is equal to L, so I am going to put it 0 and L. The particle always exists between 0 and L, so this must be equal to 1. However, I have not yet obtained the wave function. So I told you earlier that the wave function, which is basically a function of both x and t, is a multiplication of the eigenfunction. So this is the eigenfunction and e to the power minus I et upon h cross. So this is basically the actual proper wave function, which is a multiplication of our obtained eigenfunction solution and the time component. Now this must satisfy the Born's interpretation. So now let's that will help us calculate the value of a. So let me put this here in this particular integral. So if I put this here, then what is this? This is nothing but a sine of n pi x upon L e to the power minus I e t upon h cross. So this is what we just now obtained. So if I put this here, this becomes a sine of n pi x upon L e to the power. Now this is a complex conjugate of the wave function, right? So complex conjugate means what? It means that the iota is replaced by negative iota. So here I will have plus iota et upon h cross, and then I have a multiplied by a sine n pi x upon L. This is just the wave function, which is e to the power minus I et upon h cross dx is equal to 1. So now this becomes a problem where I need to solve this integral. So to solve this integral, I take a outside, so this becomes a square, and then I get sine square n pi x upon L. Now here these two terms get cancelled because they are e to the power plus I and e to the power minus I. Now this becomes dx is equal to 1. So to solve this integral, we can apply some kind of a trigonometric identities. For example, sine twice theta is equal to twice of sine square theta minus 1. So this is 1 plus sine twice theta divided by 2 is equal to sine square theta. So if I apply this here, then I can simply rewrite this integral as half of 1 plus sine of twice n pi x upon L dx is equal to 1. So let's try to solve it further. So here I can separate both these two terms. So I can say a square upon 2 integration from x is equal to 0 to L dx plus a square by 2 integration from x is equal to 0 to L sine twice n pi x upon L dx is equal to 1. The first term here is easy, a square by 2, just x from 0 to L. The second term is also easy, a square by 2 multiplied by inverse of the constants, which is L upon twice n pi, integration of sine twice n pi x upon L, which is just, what is it? This is negative of cos twice n pi x upon L from 0 to L. This is equal to 0. So now if I apply the limits, then this simply becomes a square by 2 multiplied by L minus a square L 4 n pi. Here I can write cos of twice n pi L upon L minus cos of twice n pi into 0 upon L is equal to 1. Now what is the cosine function? If you look at the cosine function varies something like this between x is equal to 0 and x is equal to, let's suppose, twice pi, alright, or twice n pi. So here this is what? This is twice n pi, right? So for twice pi, for 4 pi, for 6 pi, this term will always have a value of what? This will have a value of 1. Now what is this? This is 0. So what is the value of cos 0? The value of cos 0 is also equal to 1. So this I get here as a square L by 2 minus a square L 4 n pi 1 minus 1 is equal to 1. So this of course becomes 0. The whole term it becomes 0. So I am finally left with a square L by 2 is equal to 1, or a square is equal to twice upon L, or a is equal to square root of 2 upon L. So finally, yes, we have obtained the constant, that a, that we have been searching for since the beginning. So here we have the eigenfunction solution that we obtained. Yes, this is the eigenfunction solution that we obtained, and corresponding to this eigenfunction solution we had the wave function solution also. Yes, so here I can put the value of a. Let's put the value of a in the eigenfunction solution, and then we can basically rewrite this as, so if you look at the eigenfunction solution psi x, this is basically equal to square root of 2 upon L sine n pi x upon L. Finally we have this, the eigenfunction solution of the time independent Schrodinger's equation, and corresponding to this we can also write the final wave function. So the final wave function is just this square root of 2 upon L multiplied by sine n pi x upon L multiplied by e to the power minus t upon h cross, where E here represents the energy. Now I'm going to talk about the energy term a little bit later on. First, let us try to graphically or visually try to understand what these solutions mean. I already told you that there are infinite solutions of the Schrodinger equation here. Why? Because n can take values of 1, 2, 3, 4, infinite values. So for all values of n, I can have an individual eigenfunction, an individual wave function. So let's represent them visually and try to understand how all of these solutions are going to be different from each other. Okay, so if you represent the eigenfunctions corresponding to n is equal to 1, psi 1, n is equal to 2, psi 2, corresponding to n is equal to 3, psi 3, and corresponding to n is equal to 4, you will find that the visual representation of them involves some sort of a figure like this. So if in the first case I get a half of a sine function, in this second case I get a complete sine function like this, in the third case I get a sine function which has two nodal points like this, and in the third case I get twice the sine function, something like this. So a proper mathematical visual representation of the wave functions corresponding to psi 1, n is equal to 1, psi 2, n is equal to 2, psi 3, n is equal to 3, and psi 4 looks something like this. If you write it mathematically, this is nothing but psi 1x is simply equal to square root of 2 upon L sine pi x upon L. Similarly, this is nothing but psi 2x is nothing but square root of 2 upon L sine of twice pi x upon L, and so on and so on. So these are the wave functions, the first four of the infinite possible wave functions for this particular problem. Let's also take a look at what is going to be the probability associated with each wave function. So I already told you that the probability is basically, if I take a wave function, I take its modulus square. This basically represents the probability of the wave function at a particular point. All right, you integrate it when you want to find it in a region, but at a particular point, this is the probability. So let's look at the probability graphs corresponding to these wave functions. So if you find the probability corresponding to each and every one of these wave functions, the first thing to note down is that probability is never going to be negative, it is always going to be positive. So the wave function can have positive as well as negative values, as you can see here, positive, negative, positive, positive, negative, positive, negative values. However, the probability is always going to be positive. It can be 0 or it can be some positive value less than 1. It will always be between 0 and 1. The probabilities, if you find out, look something like this. The probability corresponding to psi is equal to 1 is something like this. The probability corresponding to psi is equal n is equal to 2 looks something like this, and the probability corresponding to psi is equal to 3 looks something like this, and the probability corresponding to n is equal to 4 looks something like this. So as you can see here, these nodal points, so this nodal point corresponds to this particular nodal point. So psi is equal to 0 here, and the probability is also equal to 0 here. These two nodal points here corresponding to these two nodal points here, and these three nodal points correspond to these three nodal points here. So this is a visual representation of the wave functions as well as the probabilities associated with the particle. The probability simply means that if you make a measurement of, let's suppose, this first wave function particle, then if you make many number of measurements, sometimes you'll find the particle somewhere here, sometimes you'll find here, sometimes here, but if you make many number of measurements, you'll find that vast majority of the time you will find the particle somewhere in the middle, and the probability of finding the particle somewhere near the edge becomes lesser and lesser. So now that we have done the visual representation, let's now look at energy levels. All right, so let's take a look at the energy levels of this particular system. To get an idea about energy levels, we go back to one of our original points that we obtained before. So here we obtained that Kn is simply equal to n pi upon L. However, I also asked you to remember this particular point where I said that K is nothing but twice root square root of twice m e by h cross square, where e is n. Now I know that K can have an infinite values, so now let's use these two equations together. So K is basically equal to square root of twice m capital E upon h cross square, or and K is also equal to n pi upon L. So from here I know that n can have many values. N can have values of 1, 2, 3, 4. So here I say that this is Kn corresponding to one particular n. Now as you will see, E can have many values also. So if I put K square and K square from here, I can say that twice m E upon h cross square is basically equal to n square pi square upon L square. Now I'm going to say that E, there is a subscript corresponding to n. For all values of n is equal to 1, 2, 3, there are different energies possible. So if I write this finally, I get En is equal to n square pi square h cross square twice m capital L square. So this is the expression for all possible energies of the particle. Now it is very important to note, first of all, there are many points here. Okay, the first point that I want to make is that this corresponds to discrete energy levels. Now what are discrete energy levels? In normal day-to-day life, a particle can have any value. There is no restriction on the values of energies that a particle can have. A particle can have some value, it can have some other value. A continuous distribution of values of energies is possible for a normal macroscopic particle in our macroscopic world. But in the quantum world, for quantum particles energies are restricted to only certain values. So whatever energies are allowed by this equation, only those energies the particle can have. The other values of energies the particle cannot have. So let us look what values are possible. So for n is equal to 1, E1 basically corresponds to pi square h cross square upon 2m capital L square. For n is equal to 2, E2 basically corresponds to 2 square, which is 4 pi square h cross square upon 2m capital L square. For n is equal to 3, E3 basically corresponds to 3399 pi square h cross square by 2m capital L square. So on and on it goes, that there are only certain energy values which are possible. Now there are infinite energy levels, but not a continuous distribution. So if you look at the energies in some sort of a, let's suppose, axis. So let's suppose if this line corresponds to E1, then another line corresponds to E2, then another line corresponds to E3, and so on and on and on. The size between these lines will increase with respect to n square. Now no other level apart from these energy levels are possible. The quantum particle can only have these allowed energy levels. So in a way, quantum mechanics for this particular problem leads to discrete energy levels. The particle is not allowed to have a continuous distribution of energies. It can only have some energy levels. Now what are these energy levels? Basically this is the energy level corresponding to psi 1. So if the particle is in psi 1 state, it will have energy E1, which is known as the ground state. If the particle is in psi 2 state, it will have energy E2. If the particle is in psi 3 state, it will have energy E3. So if I go back to my visual representation, the particle here is basically the particle corresponding to energy E1, the particle here corresponding to energy E2, the particle here corresponding to energy E3, and the particle here corresponding to energy E4. So all these particles, which are basically, these are not many particles, this is just one particle, but this one particle can have different energies, and corresponding to these different energy levels, it can have a different wave function and a different probability distribution. Now this is where some of us technically end the discussion on the particle in an infinite potential well. However, let me take some more time. If you have stuck with me till now, let's take some more time discussing the properties of the eigenfunction. All right. So some of the properties of the eigenfunctions are that the eigenfunctions are alternatively even and odd with respect to the axis passing through the origin, or with respect to the center of the well. Now what does this mean, that they are even and odd? So let me redraw the wave function again. So if I look at the first ground state wave function, and if I look at the first excited state wave function, the ground state wave function was like this, and the first excited state wave function was like this. Now if I draw an axis passing through the center of the well, then you can see that both sides of the wave function are mirror images, except in the first case the mirror image is exact mirror image, while in the other case the mirror image is inverted by negative. Let me explain this a little bit further. If this axis was center, if this axis was the center, let's suppose if this was x is equal to 0, and if this was x is equal to L by 2, and if this was x is equal to minus L by 2, although we did not perform our calculations with this, we suggested that this is 0 and this is L. However, you can do the same calculations with a problem, starting with taking the center of the well as x is equal to 0 and plus L by 2 and minus L by 2 as being the boundary. So the problem is exactly the same, although we have just taken the boundary to be at a different location. If we did this, in that case you would say that for some negative value of x and for some positive value of x, so if I take psi of minus x, then this is exactly equal to psi of x. Why? This is psi of x and this is negative of psi of negative x are exactly equal. Now this is known as even a function. On the other hand, here if we made the same assumptions, for some wave function at a negative value and for the wave function at a positive value, we'll have a negative symbol associated with this. So if I take psi minus x, so this is psi minus x and this is psi of x, then this will be related by minus psi of x. So these are known as odd functions. That means this wave function around the axis passing through the center of the well is a mirror image of itself, while this wave function around an axis passing through the center of the well is a mirror image but inverted by a term of minus symbol here. So you can see that these are these eigenfunctions are alternatively even and odd. So this is an even function. As you can see here, this will represent psi x is equal to sin x minus x. This is an odd function, this is an even function, and this is an odd function, and on and on. So this is odd because you can see here this is odd, this here will be an even function, and this here will represent an odd function. So this represents a continuous or an alternative even and odd functions in the solution. Second, the nodal points increases for n is equal to 1, 2, 3, 4 and on and on. So let me go back and I'll show you what I mean by that. So if you look at this point here, how many nodal points are here? No nodal points. There is a nodal point here which is 1. There is a nodal point, there is 1 and 2 nodal points here. There is a 1, 2 and 3 nodal points here. So similarly, you will see that for n is equal to 1, there is 0 nodal point. For n is equal to 2, there is 1 nodal point, and n is 3, 2, 3 like that. So for all wave functions, the nodal points keeps on increasing. Next, these wave functions has a property, or these eigenfunctions has a property, that if you multiply one wave function or one eigenfunction with some other and then you integrate it, then this is always going to come out to be 0. Now this will only true if you do it with different eigenfunctions. So if I take psi I and psi j, where I is not equal to j, in that case an integration of the eigenfunctions and integration of the product of the eigenfunctions will always come out to be 0. This property is basically known as the property of orthogonality. Now this is a very important property, but I'm not going to discuss this any further because the video is going to be very long. So I'm not going to derive how this comes out to be 0, but if you're interested, maybe you can check out a book. So this is will always come out to be 0. And finally, if I write the actual wave function solution, so if I write the actual wave function solution, I told you that the wave function is a product of the eigenfunction, which is square root of 2 upon L sine n pi x upon L e to the power minus I et, where E is what? E, we just found out that E is this particular expression, n square pi square h cross square by 2 ml square. So I can write n square pi square h cross square by 2m capital L square et upon h cross. So now this entire expression contains all the information about all the infinite possible wave function solutions. So there is a wave function corresponding to n is equal to 1, there is another wave function corresponding to n is equal to 2, there is another wave function corresponding to n is equal to 3, and they are all distinguished by different energy levels. So now before you make a measurement, it is possible for the particle to be any one of these wave function solutions, or it is possible for the particle to have any one of the possible energy levels. So the general wave function is basically written as a linear superposition of all the infinite possible wave function solutions. So the general wave function, the complete wave function, is written as a linear superposition from n is equal to 1 to n is equal to infinity, and if I multiply this with some constant Cn, then Cn simply refers to a coefficient corresponding to every single possible wave function state. So Cn basically gives us an idea about what is the probability. If you make a measurement, what is the probability that a particle is going to be in that wave function state. So if you make a measurement on a similar system many number of times separately, then some of the times the particle is going to be in one wave function state, some of the other times it is going to be in another wave function state. So Cn basically gives us an idea what is the probability that your measurement will give you a given wave function state. So let's make a revision. This was a very long video, so let's make a revision of everything that we have done till now. So we started with this particular problem of particle in a box. I said that the general Schrodinger's equation can be converted to a time independent form for when potential is independent of time, and in this case the wave function is basically a multiplication of the eigenfunction solution, which is a solution of this and this particular time component. And then later on we applied the potential is equal to 0 here because we are only evaluating the Schrodinger's equation inside the well. This gave us this equation whose solution is this. Now next is the problem of applying boundary conditions to find A and B. If I apply boundary conditions, B comes out to be 0, and I also, if I apply the second boundary condition, I end up getting the expression for K. Alright, so if I put the expression for K here, this is the eigenfunction and this is the wave function solution where the eigenfunction is multiplied by the time component. Now this wave function must also satisfy the bond statistical interpretation. So if I apply the bond statistical interpretation, then I come up with the value of A. So finally the eigenfunction is this, where there is a coefficient of square root of 2 by L multiplied by the rest, and then this is the wave function solution. If I represent all of this graphically, then I get this beautiful graph. These are the separate eigenfunctions corresponding to different states of n is equal to 1, 2, 3, 4, and this is a probability distribution corresponding to n is equal to 1, 2, 3, 4. Similarly, I also get expressions for different energies. So E1, E2, E3, E4, these are all discrete energies that the particle can have when they are in these different wave function states. Finally, I've discussed properties that these eigenfunctions are even and odd alternative. They have nodal points increasing, and they have orthogonal property, and the complete solution is given by this. So this is all for today. I hope you learned something from it. This was quite a lengthy video. I hope you enjoyed the video. Thank you very much. See you in the next one.